Alright, so welcome back to this channel. In today's class video, I'll be taking you guys state of matter, okay? And these are the outlines for the class. Now, the very first part is introduction to state of matter. The second part is gas law, while the third part is variable used to describe gas behavior, okay? So I'll first talk about this, then I'll talk about this, then before we do gas law as a whole, okay? So now let's start. I know you guys know the definition of matter. Matter is anything that has mass and occupies space, right? Yes. Now there are three states of matter. Yes, there are three states of matter: solid, liquid, and gas. Yes. Now what are the properties of solid? Properties of solid is that okay, properties of solid is that the particles in solid, they are closely packed together. Yes, they are closely packed together. Yes, they're closely packed together. Solid, they have definite shape as well. Yes, the particles are closely packed together. They have definite shape as well as definite volume. Okay. Yes. Now what about liquid? Now in liquid, the particles, they are still close, but not as close as the particles of solid. Okay. So in liquid, the particles of liquid, they are close, but they can move. Yes, they can move. But in solid, the particles are close. They are close. They are closely packed together. They don't move. They only vibrate about their position, but they don't move. They have definite shape and volume. But if you look at the particles of liquid, the particles are close. Yes, they are close, but not as close as the particles of solid. And apart from that one, these particles, they move. Yes, they move. And also liquid, they have definite volume, but no definite shape. Okay. Yes. Then gas. Yeah, the particles, they are far apart from each other. They are far apart from each other. They move. Yes, and they have no definite shape. Okay, so this is all about um, state of matter. Yes. The next part is gas law. Yes, but I will jump this and move to this first. We'll talk about this before we do gas law. Okay. So the variable used to describe gas behaviors. What are the variables used to describe gas behavior? Pressure, temperature, and another one, volume. Okay. So where is pressure generally? Pressure is what? Pressure is force per unit area, right? Let me put this part. So pressure is force per what unit area, right? Yes. Now what is the SI unit for pressure? The SI unit for pressure is Pascal. Okay. Yes. Now please, this part is very important because I'm going to use them while calculating. Okay. So the SI unit of pressure is Pascal, which is in short form, which is PA. Okay. Yes. Now take note that 1 Pascal this is very important. 1 Pascal is still, apart from that one, Pascal, the SI unit of pressure is Pascal. Yes, the other unit of pressure can also be Newton per meter square. Okay. Yes. So take note that 1 Pascal is equals to 1 Newton per meter square. Okay. Newton per meter square. This one is still something as Newton nm minus 2, right? Yes. So 1 Pascal is equals to what? Is equals to 1 Newton per meter square. Now let's move further. 1 atmosphere. These are the units used to measure Pascal, Newton per meter square, atmosphere, millimeter mercury, torr. So these are units used to measure pressure. Okay, they are different units. So this part is very important. Okay, please. We all know that 1 Pascal is equal to 1 Newton per meter square, right? Yes. Then also one atmosphere is equals to 760 millimeter of mercury. Yes. And also this 760 millimeter of mercury is still equals to 760 torr. Okay. So that will tell you that if 1 atmosphere equals to 760 millimeter mercury and 760 millimeter mercury is equals to 760 torr, so that will tell you that 1 atmosphere is still equals to what? Can also be still equals to what? 760 torr. Yes. It's still equals to 760 torr. This is very important. Now apart from that one, 1 atmosphere is still equals to what? 1 atmosphere is still equals to 1.013 times 10 raised to power 5 Pascal. Okay. Yes. If you look at this, please, 1.03 times 10 raised to power 5 Pascal or Newton per meter square. Remember, 1 Pascal is equal to 1 Newton per meter square. So since 1 Pascal is equal to 1 Newton per meter square, if one that means 1.0013 times 10 to the power 5 Pascal can also be still same thing as well 1.03 times 10 to the power 5 Newton per meter square. So 1 atmosphere can also still equals to what? 1 atmosphere still equals to what? 1.013 times 10 to the power what? 5 Newton per meter square. Because why? Because 1 Pascal is equals to what? 1 Newton per meter square. Therefore, if 1 atmosphere is equals to 1.013 times 10 to the power 5 Pascal, therefore 1 atmosphere can still be equals to what? This, because these two they are equal. So that is just it. So these are the important things you need to take note of under pressure. Okay, yes, 1 Pascal equals to 1 Newton per meter square. 1 atmosphere is equals to 760 millimeter mercury. Still equals to it's still equals to 760 torr. Then 1 atmosphere is still equals to 1.013 times 10 to the power 5 Pascal, or 1.013 times 10 to the power 5 Newton per meter square. So this is very important. Okay, yes. Now let's move to temperature. Temperature is still another temperature is still on another variable used to describe gas behavior. Temperature, what is temperature? Temperature is measure of the degree of hotness or coldness of a body. Okay, yes. So the SI unit of temperature, we all know that temperature is measured with the SI unit of temperature is Kelvin, right? Yes. Now to convert from Celsius to Kelvin is very easy. Temperature to come in Kelvin is equals to what? The temperature in Celsius plus 273. What is this telling you? Well, this is telling you that, let's say for example they give you 25, let's say for example they give you, let's say they give you 10 degree and they tell you to convert it 10 degrees Celsius, and they tell you to convert it to Kelvin. It's very easy. Take the 10 degree here, 10 take 10 take the 10 degrees Celsius here, then add it to what? 273. You get your temperature in what? In Kelvin, right? Which should not be 283, right? 283 Kelvin. So it's very easy. Okay, now let's move to the next variable, which is volume, before we move to gas law. Let's continue. Okay, so let's continue with the third variable, which is volume. Okay, now what is the volume? What is volume? Volume is the space occupied by gases. Yes, that space occupied by gas is known as volume. Okay, yes. Now the unit of volume, the different units of volume, we have liter, milliliter, cm cube, dm cube, right? Yes. Now please take note of this part. This is very important. Okay, yes, just take note that 1 liter 1 liter is equals to what? 1 dm cube. Very important. Okay, 1 liter is equals to 1 dm cube, because most of the things we are going to use to solve is maybe will be in the most of the volume we use to solve will be in liter. Okay, just know that 1 liter is something as what? 1 dm cube, which is something as what? 1000 centimeter cube. Then we still 1000 centimeter cube, which still equals to 1000 milliliter. Okay, which is equals to 10 to the power minus 3 m cube. Okay, so majorly just take note of this. This is very important. Okay, you can still take note of this once. Okay, but just know that 1 liter is still the same thing as, it still equals 1 dm cube. Okay, so now let's move to the gas. Let's move proper to the gas law. Different types of gas, different gas laws. We have Boyle's law, Charles law, lussac law, Avogadro law, gas law. Then Dalton laws of partial pressure, then Graham's law of diffusion and effusion. Okay, so now in these two parts, Boyle's law and Charles law will be very, very fast, because I think most of us know that one. Okay, Boyle's law, we state that the volume of given mass of gas is inversely proportional to its pressure, provided that temperature remains constant. Right, that is under Boyle's law. Instead that volume of a gas of given mass of gas is inversely proportional towards to its pressure at constant temperature, right? So temperature and temperature and number of mole is constant. Okay, Km is constant. So this is Boyle's law. Okay, you know the formula, V1 P1 equals to V2 P2, right? Yes. So I'm not going to waste time here. Then what about Charles law? Okay, so we all know that in Boyle's law, volume is inversely proportional to pressure, and temperature and the number of mole of that gas is constant. Okay, then what about Charles law? Charles law states that volume of given mass of gas is largely proportional to its temperature in Kelvin, provided that the pressure remain constant, right? That is, volume is very proportional to temperature in Kelvin. The pressure and number of mole, okay, will come in. So Sharp's law said that the volume of a given mass of gas is very proportional to what? The temperature in Kelvin, provided that the pressure and number of mole is what? The number of mole is constant, right? Yes. So in Boyle's law, pressure volume is inversely proportional to pressure. What does this mean? When you say something is inversely, when you say A is inversely proportional to B, and A is directly proportional to B. There are two different things. Okay, A inversely proportional to B, A directly proportional. This one here is inversely proportional, while this sign means directly proportional. Okay, this is inversely proportional. This is what? When something like this. This is inversely proportional. Okay, okay, B. This one means that A is inversely proportional to B, while this one means that A is directly proportional to B. Now, what does it mean? It means that as A is increasing, B will be what? Decreasing. Then as A is decreasing, B will be what? Increasing. Now, but for directly proportional, for directly proportional, it means that when one is increasing, the other one will still be increasing, right? When one is decreasing, the other one will still be decreasing, right? So if A increase, B increase. If A decrease, B decrease. So that is for directly proportional. When two quantities are to directly proportional, it means that anything that happens to one of the quantity happens to the other one. If one increase, the other one increase. If one decrease, the other one decrease. Okay, but in inversely proportional, when you say two quantities are inversely proportional, it means that when one is increasing, the other one will be decreasing, right? So what happens to this one? The opposite will happen to this. Okay, so if this one increase, this one will decrease. If this one increase, this one will decrease. So that is it. So that is telling you that in Boyle's law, as the volume of a gas increase, the pressure will decrease, and as the volume decrease, the pressure will also increase. But in Sharp's law, volume is highly proportional to temperature. So as the volume of the gas increase, temperature increase. As the volume of the gas decrease, temperature decrease. So that is just it. Okay, so you know the formula for Sharp's law. V1 T1 is equal to V2 over T2, right? So I'm not going to spend time in this place. Okay, now the law state that, let me just write this. The law said that when gases react, guys, the Loza law said that when gases react, they do so in volume. They do so in volume which are in simple whole number ratio. Which are in simple whole number ratio to one another. Okay, when gases react, they do so in volume which are in simple number ratio to one another, and to the volume of the product, and to the volume of the product if gaseous. This is very important. If gaseous, provided that provided that provided that temperature and pressure remain constant, right? Provided that temperature and pressure remain constant, right? Remain constant. Okay, so now we explain. Okay, then before I continue the Lussac law, I will also state, let me state Avogadro's law. Okay, Avogadro's law state that different volume, okay, different volume. Okay, no, Avogadro law said that equal volume, yeah, equal volume of different gases of different gases. Okay, equal volume of different gases at constant temperature and pressure. Okay, at constant temperature and pressure. Okay, equal volume of different gases at constant temperature and pressure contains equal number of molecules. Contain equal numbers of molecules. Okay, or mole. Okay, molecules. Okay, so this Avogadro's law. Then why this is the Lussac law. Okay, so now let me clean this part. Okay, so now why is this law? Let me start with Lussac. What is this law talking about? Okay, and what is Avogadro's law talking about? It's very easy. Okay, now let's go to the law again. Now Avogadro's law states that when gases react, they do so in what? In volume which are in simple whole number ratio to one another, and to the volume of the product if gaseous, provided that temperature and pressure remain constant. This law is very easy. The law is saying that when gas react, um let me use let me use hydrogen reacting with oxygen to form, let me use this side. Okay, hydrogen reacting with what? Oxygen to form water. Okay, so this reaction, okay, let me see, is balanced. All right. So now, now what is the Lussac law saying? The Lussac law is saying that when gases react, they do so what? They do so in volume which are in simple whole number ratio to one another, and the volume of the product if gaseous, provided that the temperature and pressure remain constant. The law is telling us that when gases, when gas, these are gases, all of them are gases, right? This is steam, okay? Steam. That is gaseous form of water. This is hydrogen. Hydrogen is a gas. Oxygen is a gas as well. Okay, so the law says, it's telling us that when gases, when they react, they do so in volume, and they do so in volume. So it's telling us that the volume in which the when the gases react, they are usually what? They are usually in whole number ratio. They are usually in ratio. I don't know if you understand. So that when gases react, their volumes with which they used to react is in whole number ratio, okay, provided that temperature and pressure is constant, okay. So that is just it. So that in, okay, they do so in volume which are in simple ratio, whole number ratio to one another. So these gases now when they react, their volumes are in whole number ratio. For example, that is, if I want to write this one now in according to the Lussac law, it's telling us that um, this is hydrogen, right? There is telling us that two volume of hydrogen react with how many volume of oxygen? One volume of oxygen, right? One volume. Then to give the two volume of what? Of water or steam, right? So that is what exactly is telling us, that when gases, when they are reacting with their volume by what? They are in whole number ratio. They are in what? They are in whole number ratio. So what are the whole number ratio of this reaction? Is 2:1 ratio, 2:1 ratio 2, right? Yes. Now look at this part. I said, okay, whole number ratio to one another and to the volume of the product if gases react. They do so in their volume, right? Which are in simple ratio to in one another. And also it will also be in simple ratio to the product if the product is a gas. If the product is not a gas, for example, let's say it is liquid, for example. I will not do something like this. So it just be 2:1, okay? Because this one is a liquid, so it will not be in, the volume, the ratio of the reactant, the ratio of the volume of the reactant will not be in ratio with the product, because the product was a liquid, okay. But if the product is a gas, it will work with the ratio of the volume of the reactant will also be in ratio with what? With the volume of what? Of the product. Okay, so that is what the exact law is telling us, that when gas react, they do so in volume. Their volume might what? In simple number ratio. So that is just it, okay. So that is all about the Lussac, okay. Telling us that the volumes of which gases react, they are what? They are in whole number ratio. Look at it, 2:1, 2:1, okay. It will also be in ratio. It will also be in whole number ratio to the product if the product is a gas. If the product is not a gas, it will not be in whole number ratio to the product. But if the product is a gas, it will be in whole number ratio to the product. Okay, so that is just the Lussac law for you. Now what about Avogadro's law? What is like Avogadro's law saying? Okay. Now Avogadro's law explain the Lussac law the more. Okay. Avogadro's law states that equal volume of different gases at constant temperature and pressure contain equal numbers of molecules. Okay. So it's Avogadro is telling us that volume is very proportional to what? To number of mole. Okay, said that equal volume of different gas at constant temperature and pressure contain equal numbers of molecule. Now let me give you guys for example. Now let's say for example, okay, two volume of I'm coming. Two volume of oxygen, okay, three volume um of steam, okay, of steam. So that one I'm going to use again. Let me say, okay, two volume of carbon dioxide. Okay, yeah. Now, which of these three gases we have the same number of mole? which of these three gas, which of these, okay, they ask which of these has the same, we have the same number of mole. A, let me not just do it. Okay, which of these we have the same number of molecule? The answer will be what? Will be these two. Okay, will be both oxygen and carbon dioxide. Because why would they have the same number of molecule? It's because they have they have the same volume. Okay, that is just it. Okay, so it said that equal volume of different gases at constant temperature and pressure contains equal number of molecules. Yes. So this tries to tell you that two volume of oxygen has the same number of molecule as two volume of carbon dioxide. Yes, we can still prove it. That is just it. We can still yes, we can prove it, and we find out that these two that has the same volume. We also have the same number of moles. Let's just prove it. Number of mole is equals to volume over 2.4, right? Now let's just prove it. Now where's the volume of oxygen? Yes, 2. That's 2 divide 2.4. Now let's do this other one. Number of mole is equals to what? Volume over 2.4, right? Now where's the volume of carbon dioxide? Volume of carbon dioxide is 2. Then divided by 2.4. 2 divide 2.4. You give us 0.089. If you do this the same, you give it will still give us 0.089. So that will tell you that gases that have the same volume, they have the same number of mole. Yeah, that is just it. Okay, so that is what Avogadro is telling us, that volume is directly proportional to mole. Yes, number of mole. Okay, so gases that have the same volume, gases that have the same volume at constant temperature and pressure also have the same numbers of molecules in them. Okay, so that is just it. Okay, so that is Avogadro's law. Now let's move deeper to this interesting part. Okay, ideal gas law equation. Okay, ideal gas law equation. Now, ideal gas law equation is very important. Ideal gas law equation is derived from Boyle's law, Charles law, and Avogadro law. Now, what is Boyle's law? Boyle's law states that volume of a given mass of gas is mass proportional to what? To its pressure, provided that temperature and what number of mole is constant, right? This is Boyle's law. What about Charles law? Charles law states that volume is directly proportional to temperature, right? Pressure and number of mole is constant. Don't worry about Avogadro law. Avogadro law states that volume of the gas is directly proportional to the number of mole. Then temperature and pressure is constant, right? Now these three laws, Boyle's law and Charles law and Avogadro law, they are derived. These three laws they combine to form ideal gas law equation. Okay, so now now we need to combine these three laws to form the ideal gas law equation. Now how we're going to do it is very easy. Okay, so normally we know that volume is inversely proportional to what? To pressure, right? While volume is inversely proportional to pressure and directly proportional to what? Directly proportional to temperature and number of mole, right? 1 times Tn give us what? Give us Tn, right? Yes. Now, according to mass, in order to remove this proportional sign we introduce equal to, right? We introduce a constant, right? Yes. So in order to remove this proportional sign, we introduce what? A constant, right? Yes. So now something like this, Ktn over what? P. So this K, which is a constant, is known as what? Is known as R. Now R is known as ideal gas constant. Okay, R is known as ideal gas constant. All right, so arrow is known as ideal gas constant. So in place of K, I'll put what? I'll put arrow. So this is the ideal gas equation. Okay, which can also, if I rearrange it, it can be V equals to N arrow T over P. Okay, so this is ideal gas law equation. Okay, now if I I'm not done yet. If we cross multiply, volume will be multiplying pressure, right? So now something like this, PV is equals to nRT. So therefore, this is the ideal gas equation, right? This is the ideal gas equation. It's gotten from both Boyle's law, Charles law, and Avogadro law. We combine the three laws to give us ideal gas law equation. Okay, so that the arrow is known as ideal gas No, it's not as a gas constant. Okay, it's not as a gas constant. Okay, so now let's get the constant. How are we going to get the constant? It's very easy. Okay, so let's do it now. Now, before I continue, just take before I continue, this is STP, which means standard temperature and what? Standard pressure, right? So standard pressure of a gas is 180 m. Yes, 180 m, 760 millimeter mercury, 760 torr. Yes, and so on. Okay. Yes, standard temperature is what? Standard temperature of the gas is 273, right? Yes, so it's 273 yeah, 273 Kelvin. Then standard pressure is 1 atmosphere or 760 millimeter mercury or 760 torr. Okay, so now let's get arrow. Let's get it. I mean, let's get arrow. How are we going to get arrow? Okay, then let's make arrow stand alone first. By dividing both sides by empty. If we divide both sides by empty, we'll be left with arrow is equals to what? PV equals to what? NT, right? So arrow equals to what? PV is equals to NT. Now, pressure. Now, this is very important. Take note. Whenever you are solving question related to gas, the gas law equation, make sure that your pressure is always in atmosphere. Okay, I'll teach you guys how to convert from atmosphere to from millimeter mercury to atmosphere, from atmosphere to Newton per meter square, and all. Make sure that your pressure is really in atmosphere. Okay, so what is the standard pressure? Standard pressure is 1 atmosphere or 760 millimeter mercury, right? Yes, 760 millimeter mercury, right? So, but when we are dealing with a gas flow, our pressure is always in atmosphere. Okay, so for 1 mole of a gas, okay, the pressure is what? 1 atmosphere, right? 10 times. Now, what is the molar gas volume? Molar gas volume is of another gas is 2.4. Okay, it's 2.4. Then divided by, now let's say we are dealing with the number of, let's say we are dealing with 1 mole of a gas. Okay, 1 mole of a gas, then times. Now standard temperature is what? 273, right? 2 times 273. This one will cancel this. So let's do it now. 1 times this will give us 2.4 normally, right? So let's say we didn't cancel anything now, for example. 1 times this will give us 2.4. 1 times 1 will give us 27.3. That means 273. Okay, so 2.4 divide 273. We have what? 0.0821. Okay. So arrow is equals to what? 0.0821. So this is the value of arrow. Okay, so this is how we get the value of arrow. Okay, so arrow is equal to, which is the gas constant is 0.0821. Okay, then this volume known as molar gas volume. Molar gas volume is equal to 2.4 liter. Yes, 2.4 liter. Remember, I told you guys that liter is 1 liter is something as what? It's equals to 1 dm cube, right? So it can also be what? 2.4 dm cube. Okay, but we are working with what? We are working with liter. So 1 molar volume is equals to what? Of a molar gas volume is equals to what? 2.4 liter. Okay, yes. So the added gas constant is equals to 0.0821. Okay, so that is just it. Okay, don't forget that volume from there's still one thing. Okay, remember formula for added gas is PV equals to what? N arrow T, right? You know arrow to be 0.0821. Right? Yes. So please, whenever you have to solve question relating to added gas flow, make sure that your volume is in liter, your pressure is in atmosphere, your temperature is in Kelvin. Okay, that is very important. Now there's still one more thing under added gas law before we move to that law of partial pressure. Now one more thing is now we know that added gas law is equal to PV is equal to N arrow T, right? Yes. Now we all know that now we want to relate this to molar gas density also. Gas density. Okay, we want to relate this with gas density. Now how are we going to relate this with the density? Now normally according in physics, where is density? Density of a substance equals to the mass of that substance over what? Over the volume, right? Yes. Now if we have to make the volume to stand alone, dV equals to mg divided by d. We have something like this. V is volume is equals to 1 mass over density, right? So in the place of volume here, we put what? We put mass over density, right? So P will now be times V is or mg over d, right? So mg over what? Density, right? Now is equals to, now n is known as the number of mole. Now what is formula? We all know number of mole from secondary school, right? Number of mole is equals to of a substance equals to equals to the given mass over what? Molar mass, right? Yes. So in the place of N, I'll put what? Mg over M molar mass, right? So in place of N here, I'll put Mg over Nm. So I'll have Mg over what? Molar mass, right? Then times arrow, then times temperature, right? Now these two things are common, so we cancel. If we cancel, we have something like this. Pressure dividing density is equals to ROT over what? Over molar mass, right? Yes, over molar mass. Molar mass, I just turn it to M, capital letter M, okay, so that you understand this molar mass. Okay, so we've gotten density, right? So let's cross multiply. If we cross multiply, we have something like this. DROT is equals to pressure times molar mass, right? Yes. Now to make density stand alone, we divide both sides by ROT. If we divide both sides by ROT, we cancel. Density will not be what? The density of a gas will not be what? Will not be D is equals to now equals to D equals to the pressure times molar mass over um, mol over I think gas constant times temperature. Okay, so this formula is used when they ask you to look for density of a gas. Okay, yes, under the gas law. So the gas law is what? PV is equals to nRT I'm not adding nRT. Yeah, this is important. This one is when density, when they are giving density in the question. Okay, so that is just it. Okay, so that is all about gas law. Okay, you know that arrow is 0.0821. Yeah, so that is just it under gas law equation. So we do questions soon. Okay, we do some calculation question. Now move to Darwin laws of, please take note of these questions, okay? Very important. Now move to Darwin's law of partial pressure and Grant's law of diffusion and effusion. Now Darwin's laws of partial pressure. Now this law state that if there's a mixture of gases or let's say if there's a mixture, state that if there is a mixture, if there's a mixture of gases, if there's a mixture of gases that do not react chemically, that do not react chemically together. Okay, if there's a mixture of gases that do not react chemically, if there's a mixture of gases in a container, okay, that do not react chemically together, the the total pressure of this mixture, the total pressure of this mixture of gas equals the sum of the individual partial pressure. Okay, individual partial pressure of the gases that makes up the mixture, that makes up the mixture. Okay, that makes up mixture. Now then let me explain that laws of partial pressure. This part, like from here to this, like from gas law to Grams law, this part, they are very important. Okay, so very, very important. Now let me explain that laws of partial pressure. Now let's say, now that law of partial pressure say that if there's a mixture of gases, let's say in a container. Now these are the three gases. Let's say this gas is A, gas A, gas B, and gas C. Now if there's a mixture of gases that do not react chemically together, okay, remember gas is the exact pressure in the container, right? When they collide with the walls of the container, the exact pressure, right? Usually exact pressure, right? Yes, when gases collide with the walls of the container, the exact pressure on the wall of the container. Okay, so like what I said gases, they do what? They usually exert pressure when they collide with the walls of the container, right? Now let's go back to the law. Say which said that if there's a mixture of gases that is not in a container that not combine, that not react chemically together, the total pressure. Remember, I told you guys that each gas they usually exert pressure when they collide with the walls of the container that they are placed in. Okay, so this gas A now, for example, this gas A now is exerting pressure on this wall of the container, which is, let's call this pressure PA. Okay, now this gas B this gas B, then there's exerted pressure on the wall of the container. Let's call this pressure PB. Okay, then what is this gas C? Okay, it's exerted pressure on the walls of the container. Okay, gas C. Let's call this pressure PC. Okay, so plus that the total now. So that if there's a mixture of gases that do not react chemically together in a container, the total pressure, the total pressure of the mixture of all these gas, total pressure of all these gas, and the total pressure of all these gas, let's call it total pressure, okay, PT, total pressure of all the gas equals the sum of the individual partial pressure. So this is the individual partial pressure of gas A, this is the partial pressure of gas B, this is the partial pressure of gas B, this is partial pressure of gas C. So the total pressure will equals to what? The individual partial pressure of the gases that makes up the mixture. So the total pressure in this whole container will be what? Will be the sum of the partial pressure of gas A, the sum of partial pressure of gas B, and the sum of partial pressure of gas C. Okay, so that is the total pressure in the mixture. So this is what that laws of partial pressure is telling us about that. If there's a mixture of gases that does not react chemically together, let's say they are placed in a container, the total pressure of this mixture of gas, the total pressure that they exert we equals to what? Their individual pressure. This A is exerting PA, C is exerting PC, B is exerting what? PB. So the total pressure in this mixture of gas will equals to what? The sum of their individual partial pressure, right? Yeah. So that is what that is laws of partial pressure is telling us. Now we are not done yet, okay? So we are not done. So total pressure is equals to what? PA, right? Plus PB, then plus what? PC, right? Yes. Now let's go back to the loser at the gas law. Remember, the gas law is what? PV is equals to what? nRT, right? Yes. Now let's make P stand alone. Divide both side by V. Divide both side by V, we have something like this, right? We have something like P is equals to nRT over V, right? So okay, so the pressure of A will be this, pressure of B will be this, pressure of C will be this, okay? Yes. So if you want to do it now be what? It's equals to what? Now be remember P is equals to nRT over V, right? So in the place of PA, I'll put what? NA. This NART over V. Remember, pressure is equals to nRT over V, right? So this one is the pressure of what? This one is the pressure of gas A, right? So this Na is the number of mole of gas A, okay? Then plus, remember, pressure is equal to nRT over V, right? Plus Nb, number of mole of gas B, then times ROT over what? Over volume, right? Then plus Nc, num number of mole of gas C, then ROT over what? Volume, right? Yes. Now, based on the fact that based on the fact that each of these gases, based on the fact that these gases A, B, C, now based on the fact that these gases they are placed in the same container. Therefore, since they are placed in the same container, they have the same volume. Yes, they have the same volume. And apart from that, since they are placed in the same container, they are affected by what? The same temperature, right? They are affected by the same temperature, and since they are placed in the same container, they have the same volume, right? Yes, we all know that R is constant for all gas, right? R is 0.0821, right? So since they have the same pressure and they have the same, since they have the same volume, and we all know that R is the same for all of them, and we know that temperature is still the same. Since they have the same volume and since they are affected by the same temperature, the formula cannot be something like this, okay? Equals to Na plus Nb plus Nc, then times ROT over V. Okay. And if you understand, if this one multiply this, we get NA ROT over A back. I don't understand. If this one multiply this, we have NB ROT over V. If this one multiply this, we have what? NC ROT over V. So it's the same thing, okay? Now the reason why I would do it like this, number of mole of A gas A, number of mole of gas B, number of mole of gas C. The reason why I do it like this because the volume of all of the gas are the same. They occupy the same volume, We know the arrow is constant for all of them. And T, the temperature of the gas in the container is still the same. So that's why I do it like this, okay? Or you can simply do it like this. You can simply do it like this or this one, anyone. Okay, so that pressure is equals to this, or you can say total pressure is equal to this, right? Okay, so that is just it. Okay, so that is other that partial pressure. Okay, and there's still another one. Okay, this is very important. Okay, so for example, if they give now, please, this is very important. Now, if that, let's say they ask you to calculate for, okay, now please make sure that you answer your pressure. I will always say this: your pressure to always be in atmosphere. That is very important. Make sure your pressure is always be in atmosphere. Your volume to be in liter. Your temperature to be in Kelvin. Very, very important. Okay. Yes. Now they will also ask you question. Yeah, just please know this formula. Now, how to expect question from this place? They'll just give you temperature, they give you volume, they'll give you number of mole of the gas. Yes. So if you look for a total pressure, just do it like this, you get your answer, or you do it like this, you still get your answer. They'll give you temperature, they give you arrow, they'll give you arrow, they give you V, they'll give you N. They'll give you number of more of each of the gas. So do it like this. You add them. You get your total pressure, or do it like this. Okay. Now, so this is one formula. Okay. So this is one formula. All right. So this is one formula. That's the same thing. Okay. Now another thing you need to know is that, eh, another formula you need to know is to calculate. Remember, I know tell you guys that total pressure equals to the partial pressure of each of the individual gases, right? Yes. Now, to calculate for the partial pressure of each of the gas, they will give you a particular question, they give you total pressure. They will ask you to calculate for the partial pressure of one of the gases. Let's say they say you calculate for the partial pressure of gas C, that is PC. How we're going to do it is very easy. Use this formula. The partial pressure of the gas is equals to the total pressure times mole ratio. Okay, times mole ratio. This formula is used when they ask you to calculate for the partial pressure of the gas. They'll give you the total pressure. They will now this number of mole. Let me tell you, number of mole is equals to the same thing as number of mole. I mean, what am I saying? Mole ratio rather. Now mole ratio is equals to the mole of the gas given over the total mole of all the gases. I don't understand. The mole of not the mole of the gas given all over total mole. Now, for example, let's say they say we should calculate for the partial pressure of gas C. For example, I will do it like this: PC is equals to total pressure times mole ratio. Now, when I get to the mole ratio, let me do okay. Now, when I get to the mole ratio, and when I get to the mole ratio is essentially as this mole ratio is equals to this mole ratio. Based on the fact that I'm looking for the partial pressure of C, and the mole ratio will not be what? Will not be the mole of gas C over the total mole of the rest gas. That is, let's say we are dealing with these three gases now, for example. This is the total pressure now. These are three gases. Now, if they have to ask us, they ask us to calculate for the partial pressure of gas C, which is PC. We will do it like this equals to total pressure times mole ratio. Now, mole ratio will be what? Will be the mole of gas C divided by the mole of what? Of gas A plus mole of gas B, then mole of gas C itself. Okay, so that is just it. So that is mole ratio for you. For example, if they say calculate for partial pressure of gas A, for example, to be PA, the here will not be what? A, the here will not be yes. Yes. If they say okay, calculate for partial pressure of B, it's not be the mole of gas B divided by the total mole of all the gases. So that is just it. Okay, so that is just it. So if you want to write it now, it might be partial pressure of gas. Let's say gas B is equals to total pressure times NB over NA plus NB plus NC. Okay, so this formula is used to calculate for the partial pressure. Okay, this will calculate for partial pressure. They will give you total pressure, and they will give you the pressure. They will give you number of mole of each of the gases. Okay, they'll give you number of mole of B of gas B. They'll give you number of mole of gas C. They'll give you number of mole of gas C. So to look for the partial pressure of gas B, Just do is total pressure times number of mole of gas be divided by total mole. So that is just it. So this is another formula. Another formula is number one. Okay, when they ask you to calculate the total pressure. Okay, this is number two. When they ask you to calculate for the partial pressure of the gas, one of the gas in mixture. Then another thing you need to know. On that last one is, whereas, for example, when they ask you that, when they tell you that the gas is collected over water. I mean, if you understand, if they ask you to calculate, they say some question, they say the gas collected over water. Now they ask you to calculate for the partial pressure of the gas that is collected over water. Now, to now be what? Total pressure will be equals to what? Partial pressure of the gas plus partial pressure of water vapor. I don't even understand. Now let's say, for example, let's say you collected a gas over, let's say you collected a gas over water. Eh? Let's say you collected the gas over water. The total pressure exerted by that mixture will be the pressure exerted by the gas plus the pressure exerted by water vapor. I don't even understand. So in such a question, they will say a gas is collected over water, calculate the partial pressure of that gas. Use this formula. Total pressure is equal to partial pressure of that gas plus what plus partial pressure of water vapor. So to look for to look for the gas is very easy. Partial pressure of the gas just like this. Pg partial pressure of the gas is equal to total pressure minus partial pressure of steam. Okay, yes. So this is another formula when they say the gas is collected over water. Okay, that is just a three formula. One, two, three. So these are the important things to know. Okay, then we'll do question. Then last part, which is Gram's law of diffusion. Okay, say that let me show you marker. Okay, so Gram's law of diffusion state that the the rate of diffusion of a gas is inversely proportional to the square root of its density, or inversely proportional to the square root of its molar mass. Okay, yes. So this is the relation. Okay, to remove proportional this to remove this, we have the constant, right? We have the constant known as k. Okay, k times 1 will still give us k. Okay, so same thing happen for it to here. Okay, yes, same thing happen to here. So it's very easy. Then what are we going to do next? To look at cross multiply, right? So if we cross multiply, we have something like this. K is equals to arrow root d, right? If we cross multiply here, we have what? K is equals to arrow root molar mass, right? Yes. So according to mass, this one equals k is equals to this, right? K is equals to this, right? So k equals to this. So if k is equals to this, that means that k itself is what? Arrow root d, right? So it's arrow root d. Here now the arrow one d root d1, arrow 2 root d2. So this is one formula. Okay. Now when we are doing molar mass, same thing happen. Arrow root molar mass, right? 1 1 2 2. So this is one formula. Okay, yes, this is one formula. Yeah, this is one formula. So that is just it. Okay, so there are many other formula, but I will just give you these ones. So this one is used when density is present, while this one is when they give the molar mass. This is the rate of diffusion, the molar mass. Okay, so this one is for the rate of diffusion of the first gas, density of the first gas, rate of diffusion of the second gas, density of the second gas, rate of diffusion of the first gas, molar mass of the first gas, rate of diffusion of the second gas, molar mass of the second gas. Yes, so that is the rate of diffusion and effusion. They have the same formula. Okay, so that is just it. Okay, the definition of diffusion. Effusion, you know the definition. Effusion is the movement of gas through a tiny hole. That is for effusion. Okay, so that is just it. So this is the formula to under grams of diffusion. R1 D1 is equal to R2 D2. Okay, now when molar mass is present, now the R1 root M1 equals to R2 root M2. So yes, you can use any of them. Yeah, you can use any of them. Okay. All right. So let me just give you one other formula. Okay, but that's if there are gas in question in exam. Now rate of diffusion, you see, is equals to volume over time. Okay, so rate of diffusion of a gas is still equals to that rate of diffusion is equals to is equal to rate is equal to volume over time. So in the place of R, we put what? We put V over T. So now you want to get something like this: V1 T1 then root D1, right? Equals to place in place of R, you put what? V2 over T2, right? Then root D2. So the same thing happen for here. Okay, so which will be same thing happen here, which will be V1 T1 root M1 equals to V2 T2 T2 root M2. So yes. These are under formula as well. Okay. So that is just it. So now let's do some questions under gas law. I think we should do 3 questions, okay, under gas laws before we call it a day in states of matter.